my PhD in Tokyo. Finished in 2016. I worked on the UV spectroparameter on the sounding rocket. And after that, I moved to Sweden, to KTH in Stockholm, at the ÖAW-Institut of Technology. I spent 2 years postdoc and then 2 years as a researcher, also doing more like electrostatic instruments. So for plasma observation, both in aura and also outside in the solar system. I contributed to JUICE. I did the calibration of one of the instruments. And after Sweden, I moved to Germany. For 2 years, I was at DLR in Munich or close to Munich, doing completely different things, in space, but more like optical atomic clocks, essentially, on navigation. And 2023, I moved here. So now I'm leading the onboard computing group, following the heritage of doing data processing unit and electronics in general. But I'm also interested in doing at least like a self-standing instrument. And one of these first attempts is Apex, and I'm very happy to talk about it today because I've been working on this for more than a year and a half together with the students, and now it's becoming a reality. So I'm very happy to. All right. So purpose of my talk is very easy. As I said, I will present Apex. So Apex is a student instrument on the sounding rocket, and I will explain the program and all of this. It's built by students from ASTG, the aerospace team Graz, which is an organization both with two Graz and uni Graz. It's a student organization. They built their own rocket for rocket challenges, but they were very interested when I presented this idea to fly a bit higher up, but what we are used to with this rocket, which will go to 80 kilometers. I will show it later. But the other aspect of this talk is to inform everyone here, especially the younger people, about the methodology of how to design a scientific instrument. So it's a bit of not teaching, but I hope you get some useful information here. So the first question is, why do we build instruments in the first place? This is a bit of a statement I will make now, but in my view, it's very important. We build instruments because our understanding of physics with a capital P is based on observation. Anything we do, any theory we have is based initially on observation. We build theory out of observation. Theory can predict the future. We can get better observation to inform this theory and test them. And this is how we improve theory and simulation. But at the core of it, our understanding of physics, even biologically, is based on observation. Our eyes, our senses, is observation of the physical world. So this is my philosophical statement. Now, there is a methodology for this. To justify an instrument, and this is what is shown here. First, you need to have a scientific motivation. You need to say, why do we want to build this instrument in the first place? What do we want to measure? And out of this motivation, maybe you can call it science question or scientific motivation, you can make requirements. The requirements are really measurement, metrics that you want to target for your instrument. And from this, you can flow down into what your instrument should do in terms of performance and what function you should have. You might have external constraint. And I will get back to it. You will get proper example because Apex is a proper example of this, which will inform finally the design of your instrument. So in our case, the motivation is aura and polarization. So I will first introduce this. I mean, it's more than that, of course, but I want just to say that I first have to introduce to you what is the aura and what is polarization. I think it's good as a starting point. So the aura is the phenomenon which is created between the interaction, due to the interaction between the solar wind and the interplanetary magnetic field, you see on the left here, on yellow here, and Earth magnetic field, which is shown in blue here. It's compressed on the day side because of this interaction, and it's elongated in the night side, as pale here. And as the interplanetary magnetic field, evolve or progress, you have magnetic reconnection happening at the day side, pushing a lot of charged particles which are trapped in the belt to the Earth poles where the magnetic field line enter the atmosphere, and same happen on the night side. This is not as choppy on my computer, but okay. And as these charged particles are accelerated by this magnetic reconnection, they funnel down into the atmosphere, interact with the neutrals, and creates the aura. Depending on your precipitation rate, if you have high energy electrons, low energy electrons, they will get stopped on top of the atmosphere, exciting an oxygen line, which is red, which you can see here, 630. If you have higher energy electrons, they can propagate further down in the atmosphere, depositing their energy lower down, and then you get the green line. And you can also have blue line from the nitrogen. So there are different colors and depends on the energy of the amount of electrons coming down and their energy. Polarization is a property of light. So light is an electromagnetic wave, and we live in a 3D space. So it can propagate in one direction, and it still has two directions perpendicular to the direction of propagation in which it can oscillate. And this oscillation can be for a given photon. You could have it as a linear. So this will be linear polarization when the plane perpendicular to the direction of propagation is this XY plane, and you trace a line, it's linear. You can have circular or anything in between, which is elliptical. Here is just an animation. Maybe it's, again, very choppy and not very nice, but you get the idea. And so this is really how I like to express it, is polarization is the degree of freedom of the electric field in this plane, which is perpendicular to the direction of propagation. Usually, a given photon has a given polarization, but when you have a light source, it creates a lot of photons, and there's no really reason for them to be coherent in one polarization. So we're all in different orientation, different polarization, and all in all, this bunch of photons, they are kind of what we call unpolarized. But some phenomenon, magnetic field or scattering, they can polarize some of the photons more, and then you have a degree of polarization which is non-zero, essentially. This is represented with this Stokes vector. So it's 4 quantities, I, Q, U, and V. I is the full intensity, so it's the amount of linear polarization vertical plus horizontal, so it's the total light, essentially it's the total intensity of the light. But Q and U are what measure the degree of linear polarization. So Q is the amount at 0 degree minus at 90 degree, and U is the same at 40 degrees. And with Q and U, you can characterize the full linear polarization vector. And then you are left over with V, which is the amount of circular, if it's left-handed or right-handed, and this is measured by V, essentially. So to give you an example, this linear polarization here would be plus U, so 45 degrees, and this one would be plus V here, because it's right-handed polarization. So it's a mathematical representation, and this will come handy later on. Now, polarization and aura, together, what happened? There are previous observations from the ground in 2008 on the red line. This is the plot on the left side here. This is a time series of the degree of polarization, so the amount of linear polarization. And they measured that the red line was about 5% or 4 or 5% of some fluctuation. So this was back in 2008. And more recently, in 2022, they measured it in the green line at about 1%, 1.5%. So both the red and the green line seems to have linear polarization. And you might ask, why does it matter? And this goes back to a bit of quantum mechanics. I will try to not butcher it here. But the oxygen atom has 8 electrons in the outer shell, in total, sorry. And the lower shell has 2, the 2s has 2, and then the 4 left are remaining in the 2p orbital. And this creates the ground state. So it's this one here, which is the same arrows here. These are electrons with the spin up and down. And when you have collision with an electron or with a neutral atom, the different processes can excite this, like the electrons here, to go to a higher stage. So it's not ionization. The electron is still on the atom and go to a higher level orbital or a different configuration. And when this stage then relaxes over time, this is quite a long timeline because it's a forbidden line. But then you get emission of green line or red line. What is important here is they don't have the same kind of quantum degree of freedom. So this has a S of 1, is the total spin number, and the other two have S of 0. What this means is that the red line, you have a transition from single to S1. This is intrinsically by quantum mechanics polarizable because you have magnetic effect which splits this quantum state. And in theory, you expect polarization, especially in the aura, because you have magnetic field, electric field, and all these effects. And some theoretical paper actually described that this could be a proxy for the local fields or the local oxygen density as well. But what is very important is that the green line, you have a transition from S0 to S0. So in theory, this should not be polarizable by at least this formalism, as much as the theoretician pushed into this problem. Of course, maybe with more thought it might be possible, but at this stage, you say the green line should not be polarized, and it was measured on the ground to be polarized. I said on the ground because this is one of the issues with previous observations. You have the aura higher up in the atmosphere, you have different processes. They could polarize the light, and then you observe it from the ground. But in between, you have the lower atmosphere. And the lower atmosphere has a lot of aerosol, a lot of, well, just higher density. And you can have scattering. Me is for the aerosol, Rayleigh is from atoms scattering. Scattering from pollutant light, even though the observation was done at night, you could have different cities far away sending light into the atmosphere. And what you observe along the line of sight here is the scattering from it, which is polarized, because scattering polarizes light. So you never know if what you measure is actually really from the aura or for something else. I mean, yeah. So what the obvious answer to this is, well, you take the instrument and you put it into the rocket. Because then you don't have the lower atmosphere. And so this is exactly what is our scientific motivation. We want to confirm this degree of linear polarization from the previous measurement, but now we do it from above the atmosphere. So we get rid of this part here. If we go up here with a polarizer, we observe the aura and we see a degree of polarization, then it has to come from the aura. So that's our scientific motivation. We can put it in our box. And from this, we can derive, okay, what does it mean? What do we actually want to do in terms of science? And this goes into the science requirement. So first, we want to measure the red and green line because with the two previous observations, more or less with a 3-degree angular resolution. So it's not a very good spatial resolution, but this is to compare with previous observation because they use 2 degrees, 3 degrees from the ground. So we don't have a high requirement on the angular resolution of the picture, but the overall aspect is what we want to measure it with a 0.3% polarization accuracy, because we want to confirm that the degree of polarization is at 1%, and we don't want the error on it to be too big. So 0.3 means we are measuring 1% plus minus 0.3, which should be enough to assess if it's true or not. We measure 0, then it will be plus minus 0.3, and then you know that it's within this boundary. To move further into the performance requirement and functional requirements, we need to better constrain what do we actually want to observe. So, okay, no, sorry, wrong transition. First, we need a rocket. So the rocket we choose is the REXUS program, which is a European program. It's led by DLR in Germany and SNSA, the Swedish National Space Agency in Sweden, together with ESA. ESA managed the whole program, but it's really these two countries contributing to it. They provide every year 2 rockets, which are the REXUS, a rocket for rocket experiment for university students, is the acronym, and the BEXUS, which are balloons, stratospheric balloons. But we are interested in REXUS here. So 2 balloons and 2 rockets per year, and students can apply, propose experiments. The rocket is shown here. You have experimental module, usually 3 to 4 in the body of the rocket, and then a nose cone with an experiment here. And then you get, it's a 1.5 years cycle, more or less. You launch in the spring. Yeah, you can fly your rocket on this.
So sorry, can you always see the aurora up there, or do you need a special night where it would?
The rocket is shown here, so it's about, I think, 6-7 meters long, something like this. And this rocket doesn't go to space technically, because space is at 100 kilometers, but it goes to 80 kilometers. It's launched from Esrange, northern Sweden, close to Kiruna, and essentially launched towards the north. This is the boundary to Norway, and this is Tromsø somewhere there, I think. This here area is the rocket range. It's full of reindeer, so you just shoot at the reindeer. And yeah, so it goes to 80 kilometers. The flight lasts about 3-4 minutes, so not too long, actually. Right, so this is one of the constraints we have. Historically, REXUS, they like to launch in the morning because then they can fly the helicopter in the afternoon and recover the payload. So they want to be a day. They launch during March, April. So this is one of the constraints we have. At least the assumption was we will launch in the morning. Early morning, but still morning. So, and now to get further down, we need to better constrain the observation. This is my transition. So what we want to observe is what this picture shows, which is from the ISS, not from a rocket. But essentially, you have the dark side of Earth, or in this case, the dark side, but you have the aurora here at the horizon, which is created by electron impact. And you might also have airglow, especially during the day, because if the sunlight hit the atmosphere, you have photochemistry and it creates airglow. And they happen to be exactly, it's the same process, so the same transition. So they have exactly the same wavelength. The airglow is not expected to be polarized, but If we launch at night, it's not so much of a problem. If we launch in the morning where the sun is there, might be a problem. To better see what we want to do is exactly this. So because we launch in the morning, if we launch early enough, the dark side, like the night side of Earth, can still be not so far away from Curna. So Curna is here. This dashed line here will be a field of view. And the aura is represented here as the auroral oval. So you always have precipitation. You always have aura, technically. I will get back to it a bit after. It's not always strong, but you always have precipitation. And you always have an oval, which is usually centered in the night side. So the sun is here along this line here at the center. So this is midday, essentially. And the auroral oval is on the other side. It's rotating around the magnetic north pole, which is around here. But you always have precipitation. And if we are here, this is a side view, we would look on the side. We might have day glow on the path of the line of sight, which is under the sun. But eventually it gets into the shadow of Earth or the dark side. At the limb, you could see the aura. And this would be some night glow contribution. Here you can see on the side view how it looks. So this is Earth curving down. The aura is at this stage here, which is at this distance. And this actually intensity here are representative from this model. So we can calculate this, which is what I've done. The aura, as I said, the precipitation varies from days to day, and this is tied to the what is called the KP index, which is it's a composite. I mean, it's a number from 0 to 9 representing the geomagnetic activity. I think it's calculated based on different magnetometer measurements from different stations around the north area, and they can predict, okay, a KP index of 0 to 3 is when you don't have much of storm, so quiet condition. And then as you go higher in number, the precipitation rate increase, and then you start to get strong aura. So this is how it is, and you can model this. So there are models which place the oval with the right precipitation. Of course, in practice, the oval is not as nice as this, not as smooth. There is a lot of patches and so on, but it gives you an idea where to look at and what would be the average intensity. And for KP1, it looks like this. So it's here. And you can see KP2, 3, 4, 5, 6, 7, 8. So as the intensity of the storms increase, the KP index increase, both the intensity, the maximum precipitation rate, this is energy per centimeter square per second increase, but also the position of the oval change. So it gets broader, gets south and south, which is why when you have a very strong storm, KP index 7 or something, you can even see aura at night. You can imagine this rotates by 90 degrees. North of Europe is here, so you could even see it here in Austria. So we have the precipitation rate, this erg per centimeter square per second. This is the total amount of energy entering the atmosphere. And to understand how much the aura will emit light, we need to have two more aspects. One is, what is the energy distribution of these electrons? Essentially, you have energy here and you have a number of electrons. We might have different energies. The integral of this curve should be the erg, essentially, the total energy. And this is something which is not so known. It changes from scenario to scenario, but we can assume it as a Maxwellian. And the second thing is the energy deposition. So for different energy, this is altitude here, and this is how much energy is deposited for a given electron energy. Lower energy, they get stopped higher up in the atmosphere because they don't have enough energy to penetrate, which is what creates the red line, for example. And higher energy electrons, they can actually penetrate further down the atmosphere, deposit most of their energy at 100 kilometers, 120, which is why you have the green line. So essentially, just to explain more, these electrons here will go deeper, and these electrons here will deposit higher up. Put everything together, you get what is called the volume emission, which is really just the number of photons emitted in a small cube per second. So in this case, it's centimeter square. And you get a profile like this for the aura, normalized to 1 erg per precipitation. Then you can scale it based on the KP index. For the red line and the green line, so the red line is higher up, as I said before, and the green line is lower. The red line is about 40 density. The green line, at least within the assumption I'm using, which is the distribution function of the electrons and so on. But we also have the airglow. This is from just different publications, so I don't have a model for this. My assumption is very simple: is if you are under the sun, you have day glow in this profile. much more intense than if you are in the shadow, which is night glow, because here you have the UV contribution, which excites way more the photochemistry. In the night glow, you still have process, so you don't have UVs from the sun, but you still have processes creating some glow, but it's much weaker. You put everything together, and you can create a field of view map. And the core intensity here is the photons per second, per degree of the sky you are looking at. This is the aura for KP index 1. You look at -80, which is to the northwest, so where the rocket was pointing. And then you azimuth an elevation. The horizon is here, a bit below here. So the aura is at the horizon. And you have the airglow, which is, you'll see always constant, which is above essentially, because all this part of the field of view has the sunlight, but at the edge here you don't. So you don't have so much day glow. Same for the red line. And for different KP index, it looks like this. So the aura changed, the airglow doesn't change because it's fixed, but the KP index increased, the aura changed location and intensity. You can see the number of the photons increasing. Now, to go even further, you need to understand what camera do we want to use. So actually, the students suggested this, to use this lucid camera. And it's very interesting because it's just camera, it's a CMOS, it has 5 million pixels, but it has a polarization filter directly placed on the pixels. So you don't need to have different filters, they are all on the pixel already. So 4 pixels here gives you this one minus this one will be Q, and this one minus will be U, so you get directly the stock parameter. They are directly on the thing. To give you an example, this is when you point the camera to a laptop. So maybe you know, but LCD screens are polarized. And with the filter, which is at 0, you get, so all these pixels here, you can extract them and make a picture. You will see the screen, but the one at 90 degrees, you don't get anything because the light from the screen is not polarized. It's polarized linearly this way, essentially. Now what you do is you have your field of view simulation, you place your camera. What does the camera see? You propagate each of these field of view of each pixel, scale it to the number of degrees that the pixel sees, and can make a simulation of the frame, the image you will take. And this looks like this. So maybe check the time. Too much. So you assume a given exposure time of your picture. Given QE is the quantum efficiency, is how efficient is your detector at converting photon into electrons. And you get a full frame like this, which counts now in electrons for this exposure time. So it's the number of electrons that each pixel will receive in the green line and red line. And you can see, so this total intensity is the sum of the aura intensity and the airglow on the right. Here you can really see that the airglow is higher up actually for the red line because it's higher up in the atmosphere, and it's above the horizon, which is here. The aura is very dim. You really have to, well, you can change the scale, but it's about a factor of 4 lower than the airglow, which is why we still, if the aura here was inside the airglow, it would be very hard to detect. So this is a limit case in the morning where we still have the aura in the dark side. Earlier would be better because the airglow will go up and we don't care anymore. Yes. And now what you really want to understand, because our measurable or observable is the polarization. So now you can say, okay, every photon from the aura that I showed before, so the number column is polarized at 1% in plus Q. The airglow is not polarized, and you can retrieve the polarization like this. So you can see this is the Q over I, so the degree of polarization. In this area where the aura is, you can retrieve about 0.8 and here about 0.7. It's a bit less than 1%. The reason for this is some airglow and they go into this Q. So it's unpolarized and you kind of dilute the signal you want to measure. But you would say from this, okay, we can still measure this something like 0.8%, still not so bad. What really matters is the uncertainty on this. And this is critical point of my talk. You want to measure the error in Q over I. If you calculate this, I will show you the equation after how it's calculated. You get very large error because, of course, you have a lot of pixels and not much flux per pixel, and you get a lot of error. What you can do is mitigate this. So essentially here, what this tells you is that we will measure something 0.7% with an error here, which is 20%. So not so good. But you can bin pixel to increase the signal to noise. As I said, our resolution is not that critical. We can 3 by 3 degrees. The image looks like this, which is not as nice, but the error gets much lower to 0.2%. This includes the photon noise and the derive. So it seems to be feasible, essentially. Now I want to explain a bit another aspect, which is polarization response of the instrument. So an instrument always modifies what you measure. Maybe it doesn't transmit all the photons, maybe it has noise, and in this case, it might affect the polarization that you measure. So how you formalize it is this way. You have the real polarization on this side, and you have a matrix which represents your instrument. It's called the Muller matrix. It affects, so it multiplies this real polarization into what you actually measure. So when I showed you before this here, here, when I retrieve the polarization here, this is assuming that the matrix is identity, but it's not true. Actually, what you measure is this in reality. And you need to quantify all this matrix to understand how your instrument might affect the polarization. So each of these terms have a different meaning. The blue one is the scaling, so it's essentially how much of the real Q goes into the Q prime. Maybe you lose some of the scaling. The crosstalks are how much of Q goes to U prime and so on. The most important one are the red one, the spurious polarization. It's how much of the non-polarized light end up being what you think is real polarization, because this is really bad. You want to measure accurate polarization, and you don't want to have random photons being transferred into fake polarization. So to retrieve the true polarization, here I'm neglecting V. Again, the colors is we want to retrieve this vector. We measure this one. This we might know from the lab, the calibration. You can do some algebra. You can also write small q as big Q divided by I. So it's the degree of polarization. You get this expression. It's just algebra. Same for you. And this is the formula you might use to say, okay, I measure Q prime, which is the vector. I know all my parameters for my matrix, and I can get the real polarization back. But as I said, what we really care is the uncertainty on this term. The way you calculate it is that you have Q is a function of Q prime and all these variables essentially here. The uncertainty on Q is the root sum square of each of the error on each of the term multiplied by the partial derivative of this formula with respect to each of the terms. It's an error propagation. It's assumed that they are uncorrelated, which is the case because the matrix is already uncorrelated. So this is complicated. You can imagine try to do a derivative of this, but it's possible. This for every term. And if you plot, this is the essence of the talk again, if you plot on the x-axis here, these are the partial derivatives. So it's the scaling of how much the error on each of the term propagate into the final term here. For low degree of polarization, below 10%, I did 3 cases here. What really matters is the Q over Q prime. So the uncertainty on the Q prime is the photon noise and digital noise, and the spurious polarization. Because whatever error you have here, they will scale with 1 into the final error. Any other thing, they scale lower because the degree of polarization is low, so it doesn't matter. So for us, we also have, on top of having enough photons to get the photon noise low enough to get a good degree of polarization, we also need in the lab to measure the spurious polarization, so how much of the unpolarized light goes into fake polarization, because this has to be calibrated. So it's not only measuring the term, but measuring the error of the term very precisely. So we will go 1-to-1 to the final error, essentially. And so this goes into our performance requirements. We want to expose for at least 1.5 seconds. These are a bit older figure. I mean, they evolved since then, but it's still the rough idea. And we want to calibrate the spurious polarization below this 0.3% because it will be part of the budget. We also can make some functional requirements, saying, for example, we want to record all the onboard data and so on. Now we have an additional constraint, which is the rocket attitude. This on the right is the timeline of the rocket launch. You have liftoff. After 26 seconds, the motor is turned out, so it doesn't push anymore. You have nose cone separation. And after that, you have a yo-yo D-spin. So yo-yo D-spin is a maneuver to kill the rotation momentum of the rocket. When you launch, the rocket is spinning for stability because you don't want the atmosphere is putting pressure on it and forces. If the rocket is spinning, it's much more stable. It's like a cylinder spinning. It doesn't take too much. But after that, maybe you don't want the rocket to spin so fast. So you have a yo-yo D-spin where you eject masses to kill the rotational momentum. But this happens before the motor separation, because you still have the motor attached, and when you separate the motor, and when you have your payload in your experiment. And this creates a residual tumbling rate, which is a bit random, up to 30 degrees per second. And this video will illustrate it very well. So this is from a previous rocket experiment 2 years ago. We had a camera. Here, you spin because during the launch. Then you have the yo-yo D-spin, perfect stable, and then the motor separation. You start the tumble. You actually might see the booster here somewhere. So now you might say, okay, it doesn't look so good. This we didn't really know in the beginning, but the rocket will be more stable. Usually you motor separate and then you yo-yo D-spin, so you don't have this problem. But they don't do this in REXUS. And you can see we have another constraint, and this is a bit like it doesn't go together. We want to expose stable for 1.5 seconds, and we are tumbling all the time, so it's not great. And this goes into the design. Exactly. So this is where it works, producing design and iterating on it to solve kind of this issue. So this is how it looks. Essentially, it's a 3-axis stabilization gimbal for the cameras. So we have 3 cameras, one with a red filter. The camera here is the camera can here. One with red filter, one with green, and one probably with no filter, just a wider field of view to see the context. It looks like this in the rocket. So it's on the top of the rocket and the nose cone. So we have most of the field of view. And we can, the purpose of the gimbal is to keep the camera stable at least the time of the exposure. A bit of the inner working. So there's a lot of things to unpack here. But we have the camera head here with the filters on top. We are connected via, so you have motors. You have 3 motors here with encoders. You can see here. The signals from the camera is routed down via cable reels. It's essentially a call of a cable that you can untangle for 1/2 rotation in both directions. So we are not able to continuously spin. Essentially, we have limitation because the overall solution would be to have a slip ring. Yeah, slip rings. Yes, thank you. But ESA doesn't like these things. So we go this way. It's easier. It's more reliable. But then we don't have a full degree of freedom. But that's okay. All the electronics will be placed under the base plate of the. So inside the rocket, we have a bit of space in the module. It's protected, and the data will be also stored here. And finally, we'll have magnetometer and sun sensor, as you can see here, around the whole experiment to try to get the attitude. Because we also need to point. So one thing is stability, we need to stabilize, but also would like to have at least an idea of the initial pointing. And this should be possible in theory, and this you have to see if it's challenging, but it's possible. A bit of sensor fusion, so you have different sensors. Most importantly, you have the sun sensor, which tell you where the sun is, so it's one vector, and the Earth magnetic field, which tells you where down is essentially. If you have 2 vectors, you can orient yourself in space. So the direction of observation will be pre-programmed before launch as a relation between these 2 vectors. And by measuring magnetic field and the sun and iteration of the gyro, theoretically, it should be possible to get an idea where this direction is as the rocket is pointing down and decide when we can take an exposure or not. After that, when the exposure is started, maybe from 1.5 to 3 seconds, we can use only the gyroscope is enough because the gyroscope tells you the rate of rotation much better than any other sensors. And this is the only thing you want to counteract this rate of rotation. You might see here that we actually, in this setup, we need the sun at least to get an idea of where one of the vectors is. The design has been iterated. We had preliminary design review in February, so we iterate on the design. And yeah, it's moving. There's also some locking mechanism concepts, because during the launch phase, it would be nice that the gimbal doesn't do random things, so it has to be locked. The initial concept was a sort of a mouse trap like this, but a bit too complicated and putting a long arm on the locking essentially, so it's not so great. There are different concepts with pin puller to lock the different axes. We just during the launch phase so that the instrument is safe, and ESA and DLR likes it, so it likes to be safe, let's say. And yeah, so this brings me to the timeline. Just a summary. So we get selected, or the student got selected in December last year. We had PDR, preliminary design review, in February. And the plan is to have a prototype in the summer where we can test the control loop, test the pointing accuracy, essentially the logic of and the motor actuation. There will be CDR in July, if I'm not mistaken. CDR is the critical design review. And after that, there will be a final model in December, or at the end of the year. And before that, or let's say before July and December, we would need to, and this is where I'm very interested in, characterize the camera, the dark current, all the noise sources from the camera, and maybe also, and most likely also the polarization response. So that might actually happen here if we manage to make a optical lab by this time. And the launch is in March, April next year. So I think when the instrument has to be ready by the end of the year, because when they integrate it into the rocket, they have all checks. It takes some time before the launch. So this brings me to my words. Time is it? To Apex, to the students, good luck. Good luck to them. It's a lot of challenges. I think it's not the easiest. Probably one of the most complex instruments that REXUS is flying. Most other instrument, they just like put a potato and heat it up in space or something. I mean, no disrespect. Yeah. But I think it's a lot of fun. It's a very nice program. It's you can learn a lot from ESA, DLR, and SSC. We'll see. I mean, if this works, we have a demonstrated we can point on a very bad rocket anywhere we want. Anywhere more? We'll see. And final words to the IVF scientist: go find some science question and make requirements, and support you how to derive it into instrument stuff. But yeah, science question. You need to think of how do you measure what you will do. Yeah. And that's it. That's the end of my.
For this excellent dive into how to design a rocket and let it fly with students. I'm sure there are lots of questions. So who wants to be first? Maybe one of the students? I see many non-students hand raising, but on the other hand, let's go first. Let's go. Yeah.
Is there a qualification program planned? So like vibration testing, thermal vacuum, or whatever, and where is this going to happen?
So some of the items were a bit already tested in vacuum to see if they don't outgas too much. The camera still has to be tested in vacuum, but I think so. First of all, I mean it is space, but it's like 2 minutes of space. So
you have to survive the launch.
The shaking is one thing, and I think if we have the prototype. In the summer, we can try to shake it and see that it at least make. So we did simulation. There is a SAM analysis already. They should resist the 20G or 4 and so on. The vibration spectrum is not so known. I mean, there is some numbers.
There is something in the
rocket manual. The US manual, there is one, yeah. But I would be surprised that it's really this or the real what you actually will experience. But you should be tested in it, and I think we can do this in the summer. At the TU Graz, probably.
Is it possible to test this on board when weather alone at 40 kilometers?
You still have some atmosphere. It will be better. I mean, it would be possible. It would be better than from the ground, but you still have significant atmosphere at 40 kilometers. The BEXIS program doesn't go very far. It goes 20, 30 kilometers. So a good stratospheric balloon, like research, can go up to 50 and stay there for weeks, which is very nice. But not the rocket, not the BEXIS balloon. BEXIS balloons are much smaller and not as good. So the rocket is easier. And the rocket is nicer. It's cooler. Anyway. Sorry.
Science question about the aurora you had in your sketches. That was only a phenomenon in the night side, where it makes sense, but is it physically really true? I mean, are the electrons only entering there, or is it?
No, there is a dayside aura. There is dayside aura. It's a thing. It's not in the model I used because they developed it for the night side and it's much easier to measure. But there is dayside aura. There are attempts actually on balloons to do it in the infrared, to measure it in the infrared because the contrast is much better and you can pick up some of the bands. But there should be dayside aura, and it's a very good good link to the sun and to whatever happened because it's directly in front. So you get the sun effect, and then you get directly the product of the reckoning.
From the physical phenomenon of the influx of the particles towards the pole, it should be actually kind of symmetric, yeah? So there's no reason that the physics is different.
It is more in the night side, I think, because there is more charged particle in the tail of the Earth. But in the day side, it's also exists, but it's not symmetric. It's day side, night side. On the side of the 90 degree, you have much less because there is no, it's really day side, night side. So it's and more in the night side, from what I understand.
From the point of view of data retrieval, so do you also have downlink, or do you store the data? How much of that is handled by the REXUS rocket? How much does the instrument itself?
You have an option to send some data to the REXUS module in live during the flight and send it down as telemetry. The budget is much less than the frame we have anyway. Has to be seen if it's used or not. The baseline is that everything is stored on a black box, so SD-RAM, SD card in metal box inside the module. So that we store everything and we recover the module. When the rocket lands, so the parachute is back, so the rocket lands head first, so our camera module might. So the base plate inside the base plate is okay. Like it will be stay inside. I mean, ideally.
Okay, I'll clean it.
If the rocket comes down and kills a reindeer, can you eat it?
So is the
barbecue.
Damage one of them, even with a car or whatever, you have to pay them. So actually, they have a big saying into this rocket range because the rocket disturbed the reindeers, and they're like, you should not launch it this time. So there's a. The reindeer, of course.
Yes.
My question is actually also regarding the launch time. I'm sure you probably asked if you could launch in the night, but I was just wondering if they have, what can be a good reason that they don't want to launch in the night?
Yeah, so after being selected, the students discussed this. They are actually interested in exploring it in the night, so launch it in the night. They should. So my understanding was that they want to recover the payload during the same day, because this is what I experienced also on even scientific, like the different people for scientific rocket. They also want this like to recover during the day. But if they say we launch at night, I mean we can still recover the day after. For us, we have to quantify if this is beneficial or not, because if you're at night or it doesn't change so much the intensity of the aura you observe. If it's far away or on top of you, it's the same light that you integrate anyway. If it's all around you, then you don't maybe need to point. You can just stabilize somewhere and get an image and then just point randomly, essentially, which is nice. It's much easier. But if there is no aura this day, which we cannot decide if there will be aura or not, you launch, and if there is nothing, so there is no airglow, no aura, you point it to nothing, which is not great. Whereas if you launch in the morning or early morning, even if there is no aura, you will still see airglow, and you will still measure part of the airglow, which should not be polarized, but it was never measured. So then we get a measurement, at least, which I think is an argument that I have, but we have to discuss this, which we have to analyze it.
Actually, add something to that. So the main problem that the REXUS mission has is there is no science hold. So if they want to launch the rocket and there is no technical reason for us not to start, we can say, oh no, we would like to wait another night until there's auroral. We would like to wait another hour. We need to know beforehand when to launch.
To say, I mean, it's a free rocket, so that's the point. Like, if this is a pathfinder, if it works, then we can probably propose it on the proper rocket, which is stabilized, launch at night, better optics, whatever. It's like when you really complete.
Concerning this rotating camera to counteract this tumbling motion. I mean, you can only turn this for a few full turns, yeah, and so you have to do it again and again, like this. And I mean, this is probably maybe testable, but it sounds like a really. I mean, you have to do it. You have to catch the right tumbling thing within seconds. Right?
Yeah,
so you have to work.
The loop, the scheduling loop on the software is not something to underestimate. It will be challenging, but it is possible. So essentially, anyway, you can imagine, like, if I want to observe here and I'm coming here, I can calculate, okay, I know the rate because the rocket, when it's tumbling, it's stable. I mean, no force on it, so it has some angular, but then you can predict. I know that in X amount of seconds, I will be able to target it. So maybe I can start pointing and then I keep it. And when it's done, I mean, I'm going this way anyway. This time I can just reset my position until the next. And I think we will have, I mean, one full rotation takes 12 seconds or something, 15 seconds, about that. And we have 100 something seconds of in space.
So you
will have
10 exposures preferentially on the same spot on the sky, yeah? If you manage.
Ideally, yes. If we would be sure that we can make sure we always observe the same spot, we could have, so you could stack the image and get better signal to noise, which is very nice. But because we're not sure of this, it would be nice that every image first has enough signal to get a picture anyway, and has enough polarization accuracy to do something useful.
So you could make a little mini map to try to have exposures on different patches of the sky during the 10 attempts or so you have.
Yes, but it might happen just because the initial pointing will be off anyway. But it would be nice that every single image is usable. Because one other strategy would be, we don't try to point, we just take exposure every 100 milliseconds all the time, everywhere. And then you end up with a lot of images for all noise, and you try to quad them. But it's very hard to quad noisy image together. You have the sensor data, you could figure out where it was pointing. But this is a very bad, let's say. It's much nicer if one frame has photons, has something, and we can work with it. So that's the target for us. And also the gimbal, I think, is a very nice engineering challenge, engineering aspect. And so.
Good. I would say we can put this very nice presentation. And I would like to announce that we have more course upcoming in the colloquial seminar spot. So next week, we will have Daniel Versagen here from the UCL London, talking about the impact of multiscale impact of kinetic electrons, of physics in space, and other physical plasma. And the week after that, we will have Aljona Blöcker give an overview about plasma environment interaction with an exoplanet spin. So I hope to see you again in full force in the coming week. Thank you again, our speaker.
Especially the signals better in
CADs ist schon wieder out. Outdated.
point
CCD, you can entire frame in a single.
yeah.
Sure, we can. I know.
Immer.
Maybe